Hello there, and welcome to the Sleepy Science Channel. Tonight, we set our sights on a world that has captured human imagination for centuries. The mysterious and hauntingly beautiful planet Mars. From afar, it glows red in our night sky, a distant neighbor that feels both familiar and completely unknown. But beneath that dusty surface lies a story that stretches back billions of years. A story of flowing water, shifting climates, and the lingering possibility that life may have once taken hold, or may still be waiting, hidden from view. As we drift through this journey, you may begin to see Mars not as a barren world, but as a place filled with unanswered questions. A planet that may once have resembled our own, and may yet hold secrets that could change how we understand life itself. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders soften. Let your breathing slow. And allow your mind to drift across the surface of another world as we explore the hidden story of life on Mars together. Let's begin. Mars may once have had everything life needed to begin. There was a time when Mars was not the frozen desert we see today. Its skies were thicker, its volcanoes were active, and water moved across the surface in rivers, lakes, and perhaps even seas. That matters because life, as far as we understand it, needs more than water alone. It needs useful chemistry, energy, and stable places where tiny reactions can repeat long enough to become something greater. Early Mars may have offered all of those at once. Rock, heat, carbon compounds, minerals, and liquid water were gathered together on a young planet still changing from the inside out. It is astonishing to imagine that while Earth was becoming habitable, Mars may have been running its own experiment in biology. Somewhere in that ancient world, in mud, stone, or warm underground water, chemistry may have taken its first trembling step toward life. Ancient Mars was wetter, warmer, and far more Earth-like than today. Look at Mars now, and it feels almost impossible. The air is thin, the cold is extreme, and the surface is dry enough to make Earth's harshest deserts seem generous. Yet the landscape tells another story. Spacecraft have photographed dry river channels, fan-shaped deltas, rounded pebbles, and minerals that usually form in water. These are not small hints. They are the remains of a planet that once behaved very differently. Rain or snow may have fed streams. Lakes may have lasted long enough for sediment to settle in layers. The surface may have had seasons, shorelines, and water moving through soil. This does not mean Mars was ever a twin of Earth, but it may once have been close enough to feel strangely familiar. The most haunting part is that this warmer world did not vanish completely. Its memory is still written into the ground. A dried Martian lake may hold clues to vanished microbial worlds. Jezero crater is one of the most important places humans have ever studied from afar. Billions of years ago, water flowed into this basin and spread into a lake. At its edge, a river built a delta, dropping mud, sand, and minerals in layered deposits. On Earth, deltas are excellent places to preserve traces of life, because they gather material gently and bury it quickly. That is why this Martian crater feels so powerful to scientists. It is not just a hole in the ground. It is an old water system with a record of changing conditions, carried forward in stone. If microbes ever lived in that lake or along its muddy edges, tiny chemical or structural traces might remain sealed inside the sediments. The landscape is silent now, but its rocks may still hold evidence from a time when Mars had standing water under an open sky. NASA found organic molecules in rocks from ancient Martian water. Organic molecules are important because they contain carbon, one of the central ingredients in known biology. They are not proof of life, because they can form through non-living processes as well. Still, finding them on Mars is deeply intriguing. Some were detected in ancient mudstone which formed when fine sediment settled in water long ago. That means delicate carbon chemistry survived inside rocks that once belonged to a habitable environment. Think about what that implies. Mars did not simply have dry dust and rusty stone. It had places where water, minerals, and complex chemistry met together and were preserved for billions of years. On Earth, those are exactly the kinds of settings where life leaves subtle traces. The discovery does not answer the great question, but it sharpens it beautifully. Mars had some of the right ingredients in some of the right places, and the search became far more serious. The rover named Perseverance collected a sample that may contain a possible biosignature. One of the most exciting discoveries from the rover's journey came from a rock nicknamed Chayava Falls. It contained unusual features that scientists found worth preserving for future study. The sample includes organic compounds, mineral patterns, and tiny spots associated with chemical reactions that, on Earth, can sometimes involve microbial life. That detail matters. It does not mean life was present. Nature can produce surprisingly similar patterns without biology, especially in ancient rocks shaped by water and chemistry. But this is exactly why the sample is so valuable. A rover can study Mars with remarkable instruments, but laboratories on Earth can examine tiny details with far greater precision. If that core ever returns here, scientists could test it with tools too large and delicate to send across space. The wonder is not that we already know what it means. The wonder is that Mars has handed us a question so specific, so strange, and so worth answering. Martian life, if it survives today, may be hiding underground. The surface of modern Mars is a difficult place for biology. Radiation reaches the ground more easily than it does on Earth. The air is thin, liquid water is unstable, and temperatures swing sharply between day and night. But underground, conditions could be different. Soil and rock can block radiation. Temperatures may be steadier. Ice may be protected from sunlight, and pockets of salty moisture might occasionally appear in hidden spaces. On Earth, vast communities of microbes live deep below the surface, far from daylight, using chemical energy from rocks and water. That earthly example opens the imagination. If life ever began on Mars, it may not have needed to disappear when the surface changed. It may have retreated downward, following water into cracks, pores, and buried habitats. The most important Martians, if any exist, may never have seen the sky. Mars lost most of its air, and its surface became hostile. The story of Mars is partly a story of escape. Long ago, the planet had a thicker atmosphere that helped shape a more forgiving surface. Over time, much of that air was stripped away into space. Mars is smaller than Earth, and its gravity is weaker. It also lost its global magnetic shield, which left the upper atmosphere more exposed to the solar wind. As the air thinned, pressure dropped. Water became harder to keep stable, and the planet cooled into the dry world we know now. This transformation is one reason Mars feels so tragic and fascinating. It may not have begun as a barren world. It may have slowly turned into one. A planet that once had moving water and richer possibilities was slowly altered by physics on a global scale. The search for life there is also a search through the ruins of a lost atmosphere. The red planet still keeps huge reserves of buried water ice. Mars may look dry, but it is not empty of water. Ice lies in the polar caps, beneath the ground and across parts of the middle latitudes. Some of it is close enough to the surface that future explorers may be able to reach it. That ice is more than a survival resource. It is a scientific treasure. Frozen water can preserve climate history layer by layer, much like ice sheets on Earth store records of ancient air and dust. It may also protect organic chemistry from some of the harsh conditions at the surface. For future astronauts, buried ice could become drinking water, oxygen, and rocket fuel. For scientists, it may reveal how Mars changed from a wetter planet into a frozen desert. The same hidden ice that could help humans live there may also help explain whether anything ever lived there before us. Tiny fossils on Mars would change humanity's place in the universe. A discovery would not need to be large to be revolutionary. It might be a microscopic structure inside ancient rock, a chemical pattern left by cells, or a mineral texture that only living communities are known to make. The size would not matter. The meaning would be enormous. If scientists found convincing evidence that life once existed on Mars, it would show that biology is not a one-time miracle restricted to Earth. It would mean life appeared on 2 neighboring planets in the same solar system. That would suggest the universe may be far more fertile than we have dared to assume. Even extinct microbes would change the story. They would make Mars not just a planet of geology and weather, but a second chapter in the history of life. A tiny fossil could become one of the largest discoveries ever made. Future astronauts may search for life beneath Martian dust. Robots have transformed our understanding of Mars, but human explorers would bring a different kind of ability. They could choose samples quickly, notice unexpected details, drill with flexible judgment, and adapt when a landscape surprises them. The most promising searches may happen below the surface, where ancient materials are shielded from radiation and weathering. Astrolabes might examine buried ice, crack open layered rocks, or enter lava tubes where time has left things more protected. This would not be casual exploration. It would require careful suits, sealed tools, clean procedures, and deep respect for contamination. The goal would be to avoid carrying Earth life into the very places we hope to study. There is something breathtaking about the possibility. One day, a human hand may lift a piece of Martian stone and hold, within it, the answer to whether life ever began on another world. Jezero Crater once held a river delta rich with possibility. From orbit, this place looks like a frozen memory of moving water. A channel enters the crater, spreads into branching shapes, and leaves behind a fan of sediment that resembles river deltas on Earth. That shape is one reason the rover was sent there. Deltas are natural collectors. They gather mud, minerals, and tiny chemical fragments from wide landscapes, then bury them in layers. On Earth, those layers can preserve delicate traces for immense stretches of time. In this Martian basin, each band of rock may represent a changing shoreline, a shifting current, or a season when water carried new material into the lake. The wonder is not only that a river once flowed there. It is that the river may have delivered ingredients from beyond the crater and tucked them away in stone, creating one of the best places to read Mars's ancient story. Gale Crater preserved ancient lake mud inside layered mountain rocks. The Curiosity rover landed in a place that looks almost like a geological library. At the center rises Mount Sharp, a mountain built from stacked layers of sediment. Those layers record changes in the crater across deep time. Near the base, Curiosity found mudstone that formed when fine particles settled in calm water. That detail matters because mud can seal information very gently. It can capture chemical clues without the violence of fast floods or crashing debris. The rover also found signs that the water there was not wildly acidic or impossible for life as we know it. It may have been a fairly mild lake environment for a time. As curiosity climbed, it moved through pages of Martian history. Lower layers spoke of lakes. Higher layers showed a world drying out. One mountain became a timeline of a planet losing its wetter youth. Mars had rivers long before Earth had complex animals. The dry channels on Mars are ancient beyond easy imagination. Many formed billions of years ago when Earth's life was still mostly microscopic and the great drama of animals, forests, and people had not begun. This gives Martian rivers a strange kind of power. They were flowing under a younger sun, across a world whose future would turn away from habitability. Their channels still cross the surface because Mars lacks Earth's active weather, oceans, and plate tectonics. On our planet, old riverbeds are often erased, buried, folded, or recycled. On Mars, they remain like abandoned writing. Some valleys twist across highlands. Others feed into basins where lakes may have formed. To look at them is to see water moving through a world that was alive with geology at a time when Earth itself was still preparing the stage for complex life. Some Martian valleys look carved by long vanished floods. Not every channel on Mars tells the story of a steady river. Some landscapes look as though enormous releases of water rushed through them with violent force. Wide outflow channels stretch across the surface, far larger than ordinary streams would carve. They suggest sudden floods, possibly unleashed when underground water broke free or ice was melted by heat from below. Imagine a sealed reservoir beneath frozen ground, trapped for ages, then released in a catastrophic surge. Water would tear through rock, carry boulders, carve streamlined islands, and race toward lower plains. The event may have lasted only a short time compared with the age of the planet, but its mark would remain for billions of years. These channels show that Mars was not only shaped by slow lakes and patient streams. It also knew moments of sudden release, when hidden water burst outward and rewrote the landscape. Ancient shorelines may mark where a northern ocean once spread. One of the boldest ideas about early Mars is that a great ocean may have covered much of its northern lowlands. The evidence is debated, but it is fascinating. Some researchers have traced possible shoreline features around the planet, as if water once stood at a common level across a huge basin. If that interpretation is right, Mars was not merely a world of scattered ponds and temporary streams. It may have held a body of water so large that it shaped climate, weather, and chemistry on a planetary scale. The northern plains are lower than the southern highlands, so they form a natural place for water to collect. A Martian ocean would have changed everything. Waves could have worked the edges. Sediments could have gathered along its floor. Even if the ocean was icy, temporary, or uneven, the possibility gives Mars a lost geography almost impossible to ignore. Mars still has minerals that only form in lasting water. Rovers and orbiters have found minerals that are difficult to explain without sustained contact with liquid water. Some of these minerals form when volcanic rock is altered over time. Others appear in deposits left behind as water evaporates. They are like chemical footprints, each one pointing to a different environment. Certain salts suggest drying basins. Some hydrated minerals show that water became part of their crystal structure. These discoveries matter because water that lingers can change rock in deep and revealing ways. A brief splash leaves less behind than a lake, spring, or groundwater system. By mapping these minerals from orbit, scientists can trace where water once pooled, flowed, soaked, or vanished. Mars does not need to tell its story in words. Its stones have been altered by contact, and that alteration is a language. Every hydrated mineral is a small confession from the planet's wetter past. Clay minerals can protect fragile organic molecules for billions of years. Clays are some of the most valuable materials in the search for ancient life. They form when water changes rock, often under conditions that can be relatively mild. Their tiny layered structures can trap and shield molecules that might otherwise break apart. On Earth, clays are excellent at preserving traces of past environments because they can hold chemical information inside microscopic spaces. On Mars, this makes clay-rich regions especially tempting. If carbon-based compounds settled into mud at the bottom of an old lake, clay minerals could have helped protect them from later damage. They cannot stop time completely, but they can slow destruction and improve the chance that something meaningful remains. This is why scientists care so deeply about fine-grained sediments. A plain piece of Martian mudstone may not look dramatic, yet it could be one of the safest vaults for ancient chemistry. Sulfur on Mars could have fed ancient microbial chemistry. Life does not always need sunlight. On Earth, many microbes use chemical reactions for energy, and sulfur can play a powerful role in those reactions. Mars has many sulfur-bearing minerals, and they point to a planet with active chemical environments. In some ancient settings, sulfur compounds may have moved through water, reacted with rock, and created energy gradients that microbes could exploit. This does not mean anything was alive there, but it means the fuel options were more varied than simple sunlight at the surface. Sulfur chemistry is especially interesting because it can operate in places where light is weak or absent, such as underground water systems. If Mars ever had microbes tucked beneath its surface, they might have relied on chemical exchanges rather than photosynthesis. The red planet's mineral record hints at a world where energy could have been hidden inside the rocks themselves. Iron minerals may record energy sources once useful to microbes. Mars is famous for its rusty color, and iron is part of that story. But iron is more than a pigment. It can change form through chemical reactions, gaining or losing electrons. On Earth, some microbes use those reactions as part of their metabolism. They do not eat iron in the ordinary sense, but they draw energy from transformations involving iron compounds. Mars has abundant iron minerals, and ancient water could have created places where different iron forms met and reacted. Such zones would have been scientifically exciting because they offer both a record of environmental change and a possible energy source. Iron can also leave visible signatures in rocks, including veins, concretions, and color bands. These features may tell scientists where fluids moved and how chemistry shifted. In the search for life, even a rusty stone can become a clue to once active environments. Carbon compounds on Mars are not proof of life. It is tempting to hear the word organic and imagine biology immediately. In science, organic simply means carbon-based chemistry. Such compounds can come from living organisms, but they can also form through volcanic processes, meteorite delivery, or reactions driven by sunlight and radiation. That is why Mars discoveries must be handled with patience. Finding carbon compounds is exciting because known life uses carbon so deeply. It is part of proteins, membranes, genetic material, and countless biological structures. Yet carbon can also exist in lifeless dust, ancient meteorites, and chemical mixtures that never become alive. The real challenge is context. Scientists ask where the compounds were found, what minerals surrounded them, how old the rocks are, and whether patterns match known biological processes. Mars keeps offering pieces of the puzzle. The hard part is knowing whether those pieces belong to life, chemistry, or both. Meteorites may have delivered organic ingredients to early Mars. The early solar system was a place of constant impacts. Asteroids and comets struck young planets, carrying ice, metals, and carbon-rich material. Mars would have received some of that delivery. These impacts could have brought organic ingredients from space and mixed them into surface rocks, lakes, and hydrothermal systems. This matters because a planet does not need to make every ingredient locally. it can be supplied from beyond. Meteorites falling into ancient Martian water may have added molecules that helped enrich the chemistry of the environment. Some impacts would have been destructive, but others may have created heat, cracked rock, and opened pathways for fluids. The same falling objects that scarred the surface might also have contributed useful materials. In that sense, early Mars was connected to a wider cosmic exchange. Its possible habitability was shaped not only by the planet itself, but by debris moving through space. Mars and Earth exchanged rocks during ancient asteroid impacts. The two planets have not been isolated from one another. When a large asteroid slammed into Mars or Earth, the impact could blast rocks into space. Some fragments traveled for millions of years before falling onto another world. This means pieces of Mars have reached Earth, and it is possible that pieces of Earth reached Mars as well. The idea sounds astonishing, but the mechanics are natural. Powerful impacts can launch material fast enough to escape a planet's gravity. Some of those rocks may stay relatively protected inside during their journey. This has led to deep questions. Could hardy microbes ever survive such a trip inside stone? Could chemistry, or even life, have moved between neighboring planets? No one knows whether biology traveled this way, but the possibility changes the story. Mars and Earth were not separate experiments. They were worlds within throwing distance of each other. Martian meteorites have landed naturally on our own planet. Some rocks found on Earth carry a chemical fingerprint matching Mars. Scientists know this because gases trapped inside certain meteorites resemble the Martian atmosphere measured by spacecraft. These stones were blasted off Mars by ancient impacts, wandered through interplanetary space, then entered Earth's sky as falling fire. Holding one is almost unbelievable. It is not a sample fetched by a mission, but a natural messenger from another planet. Martian meteorites allow laboratories to study pieces of Mars directly, with instruments far more advanced than anything that can fit on a rover. They have revealed details about Martian volcanoes, minerals, water alteration, and atmospheric history, yet they also come with limits. We usually do not know exactly where on Mars they came from, and their journey can change them. Even so, they prove something wonderful. Mars has already touched Earth, quietly, in the form of stones that fell from the sky. A famous Martian meteorite once sparked worldwide life debates. In the 1990s, a meteorite known as Allen Hill's 8400 became one of the most talked about rocks in history. It came from Mars and contained tiny structures, carbonate minerals, and chemical features that some researchers argued might be linked to ancient microbial life. The announcement captured global attention because it suggested that Mars may once have been inhabited. Later studies challenged that interpretation. Many scientists concluded that the features could be explained without biology. Still, the debate was enormously important. It showed how difficult the search for life can be when evidence is tiny, ancient, and open to several explanations. It also sharpened the standards for future discoveries. A claim this extraordinary needs multiple lines of evidence that fit together cleanly. The meteorite did not settle the question, but it made Mars feel closer, stranger, and more alive with possibility than ever before. Mars may have been habitable before Earth became stable. Early Earth was not always a comfortable cradle. It endured heavy impacts, widespread volcanism, and dramatic changes as its surface settled into long-term stability. Mars, being smaller, may have cooled faster. That means it might have developed solid crust, surface water, and habitable environments very early in solar system history. This possibility is startling. For a window of time, Mars may have been a better place for life to start than Earth was. Its lakes, crustal heat, and chemical diversity could have formed while our own planet was still recovering from violent beginnings. If life can emerge quickly when conditions are right, then Mars may have had a genuine chance. The question becomes almost haunting. Did biology begin there first? Did it fail, retreat, or leave no trace we have yet recognized? Early Mars may not be a dead footnote. It may be part of life's opening chapter. Early Mars had volcanoes, lakes, impacts, and changing climates. A habitable world is not always calm. In fact, early Mars was dynamic in ways that could have created many different environments at once. Volcanoes released gases and heat. Impacts shattered crust and made basins. Lakes gathered sediment. Groundwater may have moved through cracks below the surface. Climate shifted over time, sometimes allowing water to flow, then forcing it back into ice or vapor. This variety matters because life does not need an entire planet to be comfortable everywhere. It needs niches. A warm spring near volcanic rock. A lake bed with protective mud. A fractured underground system rich in chemical energy. Early Mars may have had a patchwork of such places. Some would have been harsh. Others may have been briefly generous. The planet's complexity is what makes it fascinating. Its habitability was not one simple condition. It was a changing mosaic of chances. Olympus Mons once rose above a potentially living world. This giant volcano is so large that its base would cover a huge portion of many countries on Earth. Its summit towers far above the surrounding plains, built by repeated lava flows over immense spans of time. Today, it is often described as a symbol of Martian grandeur, but its deepest significance may be environmental. Volcanic regions can provide heat, minerals, gases, and underground pathways for fluids. On early Mars, such ingredients could have influenced local habitats. The volcano itself may not have been a place where life thrived at the surface, especially during eruptions, but the surrounding crust may have held warm pockets and chemically active groundwater. A mountain of fire rising over an ancient, changing planet gives Mars a dramatic scale. It reminds us that possible life there would not have existed on a bland world. It would have shared a planet with the largest volcano known. Martian volcanoes may have warmed the planet through greenhouse gases. Ancient Mars received less sunlight than Earth, so keeping water liquid was a challenge. Volcanic eruptions may have helped by releasing gases into the atmosphere. Carbon dioxide, water vapor, sulfur compounds, and other volcanic emissions can affect climate. In certain combinations, they may have trapped heat for periods of time or triggered warming after cold stretches. This could help explain how rivers and lakes formed under a faint young sun. The warming may not have been constant. Mars may have moved through episodes with volcanic pulses thickening the air or altering chemistry, then colder conditions returning later. That stop-and-start pattern fits a world where water appears in many places but does not require a permanently warm climate. Volcanoes were not only builders of mountains. They may have been climate engines, breathing gases into the sky and giving surface water temporary chances to flow. Underground heat could have kept hidden water liquid for ages. Even when the Martian surface became cold, the interior still held warmth. Heat from radioactive decay, leftover formation energy, and volcanic regions could have warmed deep rock. If ice or groundwater existed underground, that heat might have kept some water liquid in protected places. This is important because surface conditions can become hostile, while subsurface habitats remain possible. On Earth, microbes live in deep rock fractures where sunlight never reaches and temperatures stay stable for long periods. Mars may have offered similar refuges. The deeper environment would be shielded from radiation, buffered against extreme temperature swings, and connected to minerals that could provide chemical energy. Such habitats would be difficult for rovers to reach, which makes them mysterious. The planet may have lost its rivers and lakes at the surface, yet still preserved hidden wet places below, where conditions changed slowly and survival may have remained possible. Hydrothermal systems on Mars may have resembled life's earthly birthplace. Some of the most compelling origin of life ideas on Earth involve water heated by rock. Hydrothermal environments provide warmth, minerals, chemical gradients, and tiny protected spaces where reactions can repeat. Mars had volcanism, impacts, and water, so it may have created similar systems. Impact craters could have heated underground ice. Volcanic regions could have driven warm fluids through fractured crust. In those settings, minerals might have acted like natural laboratories, helping simple molecules interact in structured ways. This does not claim life began there, but it shows why these environments are so exciting. They combine several needs in one place. Energy flows. Water circulates. Rock offers surfaces and ingredients. If biology ever emerged on Mars, hydrothermal settings would be among the most reasonable places to imagine its beginning. They give the red planet a connection not just to habitability, but to the deepest question of how lifeless chemistry becomes alive. Deep cracks in Martian rock may have sheltered ancient microbes. A planet does not need a friendly surface everywhere to offer refuge. Beneath Mars, fractures in stone may once have formed a hidden world of narrow passages, damp minerals, and chemical exchange. Water moving through these cracks could have carried dissolved elements from one layer to another, creating tiny gradients that microbes might have used for energy. On Earth, deep rock life can survive in places with no sunlight at all. It grows slowly, clings to mineral surfaces, and depends on reactions between water and stone. Mars may have offered something similar during its wetter eras. Impacts, cooling crust, and volcanic stress all could have opened pathways underground. These spaces would have been shielded from harsh surface radiation and sudden temperature shifts. If Martian life ever existed, the deepest story may not be written on open plains. It may be tucked inside stone, where darkness became protection. Mars may have offered life protection beneath its dusty crust. The top layer of Mars is harsh, but even a little depth can change everything. Dust and soil can act like a blanket against damaging radiation, especially when material is buried under rock or ice. For ancient organisms, this cover may have mattered as the planet slowly lost its atmospheric protection. Microbes, if they existed, would not have needed shelter that looked dramatic. A thin layer of sediment, a buried clay bed, or a shaded pocket beneath rubble could have made survival more possible. The crust also contains minerals that can store water or hold chemical traces. Over time, winds may have covered older surfaces with fresh dust, sealing pieces of the past away from direct exposure. What looks like lifeless ground from above may be layered with buried histories. Mars may have hidden its most important evidence not in grand mountains, but beneath ordinary dust. Surface radiation breaks apart delicate biological molecules over time. Mars is bathed in radiation that Earth's atmosphere and magnetic field would normally soften. That makes the exposed surface a difficult place for fragile chemical clues to last. Organic molecules can be damaged as energetic particles strike the ground, breaking bonds and changing structures that scientists might otherwise recognize. This is one reason the search for ancient life cannot rely only on what lies in plain sight. A rock sitting at the surface for millions of years may have had its most delicate evidence altered or erased. The same sample, buried just beneath protective layers, could tell a clearer story. Radiation does not make discovery impossible, but it changes the strategy. Scientists must think like detectives arriving long after the event, searching for places where the evidence was shielded. On Mars, the best clues may survive only where the planet itself has kept them covered. buried sediments are better places to search for ancient life. Sediment can behave like a time capsule. When mud, sand, or fine mineral grains settle in water, they can trap fragments of chemistry between layers. If those layers are buried, they may be protected from wind, sunlight, radiation, and later surface reactions. This is why ancient lake beds and deltas matter so much. They do not merely show that water was present. They can preserve a record of what the water carried. On Earth, some of the oldest signs of life are found in layered rocks that formed in watery environments. Mars offers similar geological settings, though their meaning remains uncertain. A buried layer might hold carbon compounds, mineral textures, or chemical patterns that formed long ago. The challenge is reaching the right depth without contaminating the sample. The promise is enormous. Beneath dull-looking rock may lie a page from a vanished environment, still readable after billions of years. The Rosalind Franklin rover is designed to drill deeper for clues. Most Martian missions have studied the surface or only scratched just below it. This rover was built with a different ambition. Its drill is intended to reach far enough underground to collect samples less damaged by radiation and surface chemistry. That matters because even the most interesting organic molecules can be altered if they spend too long exposed. A deeper sample may preserve a cleaner record of ancient conditions. The mission is also named for a scientist whose work helped reveal the structure of DNA, which gives the rover's search a fitting sense of history. It is designed to examine minerals, chemistry, and possible traces of ancient life in ways that complement earlier missions. The exciting part is not simply that it can drill. It is that it can choose places where the subsurface may have protected the faintest clues. Mars may require us to dig before it speaks. Mars dust contains perchlorates that challenge life and astronauts. The dust on Mars is not just dry powder. It contains reactive salts called perchlorates, which complicate nearly every dream of living there. For biology, these compounds can be difficult because they may interfere with cells and damage organic molecules under certain conditions. For human explorers, they could create health concerns if dust is tracked into habitats or clings to suits and equipment. Yet perchlorates are not only obstacles. Some microbes on Earth can use related chemistry, and the salts can lower the freezing point of water, which raises questions about brief, salty moisture in the soil. They may also be useful in future resource systems if handled safely. This is what makes Mars so fascinating. The same chemical that creates danger may also reveal hidden environmental behavior. Its dust is not passive. It is active, reactive, and woven into both the planet's hazards and its possibilities. Some Earth microbes can tolerate salts resembling Martian chemicals. Life on Earth has a habit of surviving in places that look unreasonable at first glance. Certain microbes live in briny pools, salt flats, acidic waters, or icy environments where most organisms would fail quickly. Some can endure high salt levels by balancing their internal chemistry, repairing damage, or slowing their metabolism. These examples do not prove that Mars has life, but they widen our imagination of what life can handle. If Martian environments ever contained salty water, they may not have been automatically impossible for biology. Salt can be hostile, but it can also help liquid water persist at lower temperatures. On Earth, microbial communities sometimes gather in thin films or protected pockets where moisture appears only briefly. Mars may have offered harsher versions of such settings. The lesson is simple and powerful. Life is not always lush. Sometimes it is microscopic, patient, and astonishingly stubborn. Briny droplets might briefly form in modern Martian soil. Today, stable liquid water is very difficult at the Martian surface, but chemistry may still create fleeting exceptions. Certain salts can pull water vapor from the air, or allow ice to melt at lower temperatures. Under the right local conditions, tiny salty droplets or thin films might appear for short periods. They would be cold, harsh, and chemically challenging. Still, their possibility matters because liquid water is central to habitability. These moments would not resemble streams, puddles, or rain. They might be almost invisible, forming between grains of soil, then disappearing as temperature and humidity changed. Such brines could also be too salty for known life, so scientists treat them with caution. Yet they show that modern Mars is not entirely static. Even in its present state, the ground may experience brief chemical awakenings, where frost, salts, and air interact in ways too subtle for the human eye. Liquid water on today's surface would vanish quickly. Place ordinary water on modern Mars, and it would be in trouble almost at once. The atmospheric pressure is so low that liquid water cannot remain stable across most surface conditions. Depending on temperature, it may boil, freeze, evaporate, or do several of these in rapid sequence. This is one reason the planet's ancient water features are so striking. Rivers and lakes required a very different environment from the one we see now. The modern surface is not simply dry because water is absent. It is dry because the surrounding conditions make liquid water hard to keep. Even when ice is present, turning it into lasting surface water is difficult. For explorers, this means water must be collected, protected, and managed carefully. For scientists, it means any search for present-day habitable conditions must look to special environments. On Mars, water is still there, but it rarely gets to behave like water. Martian ice may preserve ancient chemistry like a frozen archive. Ice can hold memory. On Earth, polar ice traps dust, gases, volcanic ash, and chemical traces from ancient climates. Mars may have its own frozen records, locked in polar caps, buried sheets, and icy layers beneath the surface. These deposits could reveal how the planet's atmosphere changed, how dust storms came and went, and how water moved between air, ground, and pull. Ice can also protect some materials from immediate destruction, especially when covered by soil or sediment. For life studies, that makes it intriguing. It may preserve organic chemistry better than exposed rock in some settings. For future astronauts, the same ice could become a practical resource. But scientifically, its deepest value may be historical. Every layer might be a season of Mars written in frost. To study it is to read a frozen diary from a planet that has spent billions of years changing. Polar caps on Mars hold layered records of climate change. At the poles, Mars stores time in stacked bands of ice and dust. These layers build and erode as the planet's tilt, orbit, and seasons shift across long cycles. Unlike Earth, Mars wobbles more dramatically over time, which can move ice from pole to mid-latitude regions and back again. The polar deposits therefore become a climate archive. Bright layers may reflect cleaner ice. Darker bands may contain more dust. Together, they record changing winds, temperatures, and atmospheric behavior. From orbit, these layered terrains look almost like pages in an enormous book. Scientists study their thickness and patterns to reconstruct past climates. The poles are not simply frozen caps at the ends of the planet. They are storage vaults for Mars's environmental history. Understanding them helps answer a deeper question. Was the planet ever stable enough for long enough to support habitable places beyond brief episodes? Mid-latitude ice could become water for future explorers. The most useful water on Mars may not be at the poles. Some buried ice appears to lie in middle latitude regions, closer to places where human missions might land. That matters because water is heavy, and carrying all of it from Earth would be costly. If astronauts can access local ice, they could turn it into drinking water, oxygen, and fuel ingredients. This changes the dream of Mars's exploration from visiting to staying. The ice may be hidden beneath soil, sometimes in sheets or deposits protected from the thin air. Choosing a landing site may therefore require balancing safety, sunlight, science, and resource access. A flat plain with nearby buried ice could be more valuable than a dramatic landscape with little usable material. In a future settlement, frozen ground may become as important as a river valley was to ancient civilizations on Earth. Mars has seasons that shift frost across the planet. Because Mars is tilted on its axis, it experiences seasons, though they unfold under very different conditions from Earth's. As temperatures fall, carbon dioxide from the atmosphere can freeze onto the winter pole as frost. Water frost can also appear in some regions, brightening the surface before vanishing again. These seasonal changes are not decorative. They are part of the planet's breathing pattern, moving material between air and ground. As spring returns, frozen carbon dioxide can turn directly back into gas, sometimes triggering strange surface activity. Dark fans, streaks, and patterned terrain may appear as gas escapes through translucent ice. Mars is often imagined as still, but its seasons prove otherwise. The planet changes color, pressure, and texture through the year. Frost advances and retreats. The air thickens and thins slightly. Even a cold desert can have a pulse. Dust storms can wrap the entire Martian globe in haze. Dust is one of the great powers of Mars. Fine particles can rise into the thin atmosphere and remain suspended, tinting the sky and changing how sunlight reaches the ground. Some storms stay local. Others grow into regional events. In rare cases, they expand until nearly the whole planet is hidden in a dusty veil. From orbit, familiar surface features fade beneath a butterscotch haze. For solar-powered missions, this can be dangerous because less sunlight reaches their panels. For climate science, it is a reminder that Mars's atmosphere, though thin, is active and dramatic. Dust absorbs heat, affects temperature, and influences weather patterns. A global storm can make the planet feel almost alive with motion, even without oceans or forests. The same dust that gives Mars its color can rise into the sky and temporarily erase the world below. Global dust storms helped end the Opportunity rover's long journey. Opportunity was built for a mission lasting only months, yet it traveled and worked for years, becoming one of the most beloved machines ever sent to another planet. It explored crater rims, studied rocks shaped by ancient water, and crossed landscapes no human eye had seen from the ground. Then a massive dust storm darkened the sky. Because the rover depended on solar power, the fading sunlight became a serious threat. Its batteries drained, and contact was eventually lost. The end felt almost personal because Opportunity had become a symbol of endurance. Its silence also showed how deeply Martian weather matters. Dust is not just scenery. It can decide the fate of exploration. The rover's journey helped reveal Mars as a world of ancient water and modern hazards. Its final challenge came not from a cliff or crater, but from the planet's own atmosphere. Martian sunlight is weaker, but still useful for life support. Mars orbits farther from the Sun than Earth, so sunlight arrives with less strength. That affects solar panels, greenhouse design, heating, and daily operations for future missions. Yet the light is still valuable. Rovers have used solar energy successfully, and future habitats could use it alongside other power systems. For plants, the challenge would be greater than simply dimmer light. They would need pressure, warmth, water, nutrients, and radiation protection. Still, sunlight remains one of Mars's most important natural resources. It marks the rhythm of each day, warms surfaces, powers instruments, and could help support controlled growing systems. The sky may be dusty, and storms may reduce brightness, but the sun still reaches the red planet with enough energy to matter. Any human presence there will have to learn the local light, not as Earth knows it, but as Mars offers it. Mars has no global magnetic shield like Earth's. Earth is wrapped in a magnetic field generated by motion in its metallic core. This invisible shield helps deflect charged particles from the sun and protects the upper atmosphere. Mars once had magnetism too, but it no longer has a strong global field. Instead, patches of ancient crust still hold magnetic traces, like fragments of a shield that vanished long ago. This loss changed the planet's future. Without broad magnetic protection, the atmosphere became more vulnerable to erosion by the solar wind. Radiation also became a bigger issue at the surface. The missing shield is one reason Mars feels like a world whose defenses were lowered over time. Its rocks remember a different past, when the interior may have been more active and the planet better protected. Those magnetic remnants are like ghostly fingerprints, showing that Mars once had planetary machinery it no longer possesses. Solar wind helped strip Mars of its ancient atmosphere. The sun does not only shine, it releases a stream of charged particles that flows outward through the solar system. When that stream reaches a planet with little magnetic protection, it can interact with the upper atmosphere and help carry particles away into space. Over immense time, this process contributed to Mars losing much of its air. The effect was not a single catastrophe. It was a slow leak, driven by physics, and repeated across billions of years. As gases escaped, the atmosphere became thinner. Surface pressure fell, warmth became harder to retain, and liquid water became less stable. This is one of the great planetary transformations in our solar system. A world that once held more promise was gradually exposed. The loss of air did not merely change the weather. It changed the destiny of Mars, turning its surface from potentially habitable terrain into a colder, harsher frontier. Maven studies how Mars continues losing air to space. A spacecraft orbiting Mars has been watching the planet's upper atmosphere with a specific purpose. Its mission is to understand how gases escape and how the sun influences that loss. By measuring particles, magnetic conditions, and atmospheric behavior, it helps connect Mars's present state to its ancient transformation. This is powerful because the planet is still losing material today. The escape is much slower than the dramatic changes of early history, but it continues. Solar storms can increase the loss, showing how closely Mars remains tied to space weather. These measurements help scientists work backward. If we know how the atmosphere leaves now, we can better estimate how it vanished over time. The spacecraft is not searching for fossils or drilling into rock. It is studying the invisible edge of the planet, where air becomes space. That boundary holds part of the answer to why Mars changed. A thicker atmosphere once helped liquid water persist. For water to remain on the surface, Mars needed more than cold ice and occasional melting. It needed air pressure high enough to keep liquid from vanishing too quickly. A denser atmosphere would also have helped trap heat, soften temperature swings, and support weather patterns that moved water around the planet. This does not mean ancient Mars was warm and wet everywhere, all the time. It may have shifted between climates, with water flowing during favorable periods. But a thicker blanket of air gives those wet episodes a physical explanation. It helps turn dry channels, lake beds, and altered minerals from isolated mysteries into parts of a larger planetary story. The atmosphere was not just background. It was the stage on which Martian water could act. When that stage thinned, rivers faded, lakes disappeared, and the surface began to resemble the frozen desert we see today. Ancient raindrops may have fallen on some Martian landscapes. Rain on Mars sounds strange because the planet is now so dry and cold. Yet some ancient landforms suggest that water may once have fallen from the sky, at least during certain periods. Valley networks branch across highland terrains in patterns that resemble drainage systems shaped by precipitation. Snowmelt may have played a role too, especially if ice gathered on higher ground and melted during warmer intervals. Either way, water appears to have moved from broad regions into channels, not only from isolated underground bursts. That changes the feeling of early Mars. It may have had skies that sometimes carried moisture, slopes that fed streams, and landscapes responding to weather over time. The image is almost startling. A world we now associate with dust and silence may once have known falling water, darkened soil, and the delicate beginning of rivers. Kaolinite rocks hint at long periods of wet weather. Some minerals are quick signatures of water, while others suggest a more patient story. Kaolinite is a clay mineral that often forms when rock is altered by sustained contact with water under relatively mild conditions. Its presence on Mars is intriguing because it may point to environments that stayed wet long enough for deep chemical transformation. This is not the mark of a single splash or brief flood. It hints at water lingering, soaking, reacting, and changing the fabric of the ground. On Earth, kaolinite can form in weathered soils where water repeatedly moves through minerals. Finding it on Mars raises the possibility that some places experienced extended wet episodes, perhaps with conditions more stable than the planet's colder reputation suggests. A pale clay deposit may look humble from orbit, but chemically it whispers about time, weather, and a surface that once endured water's slow touch. Mars may have cycled between habitable and hostile eras. The planet's past was probably not a simple journey from warm to cold. Evidence points to a more complicated rhythm. There may have been windows when liquid water flowed, followed by long, dry intervals, then renewed episodes of melting, flooding, or lake formation. Volcanism, impacts, orbital changes, and atmospheric loss could all have pushed the climate in different directions. For possible life, this matters deeply. Biology might have had chances to appear during favorable times, then needed refuges when conditions worsened. On Earth, organisms can retreat into dormancy, underground habitats, or protected niches during hardship. Mars may have demanded such strategies early and often. This shifting history makes the search more difficult, but also more fascinating. We are not looking at one ancient Mars. We are looking at many versions of Mars, each with its own opportunities and dangers. Habitability does not mean life definitely appeared there. A place can have water, energy, and useful chemistry without ever becoming alive. That distinction is essential. Scientists use the word habitable to describe conditions that could support life as we know it, not proof that life actually existed. Early Mars may have had lakes, minerals, carbon compounds, and heat. Those ingredients make it promising, but biology requires an origin. No one yet knows how easily lifeless chemistry becomes living systems. It may happen whenever conditions are right, or it may be extremely rare. Mars is powerful because it tests that mystery close to home. If it was habitable but lifeless, then habitability alone is not enough. If it was habitable and alive, then life may arise readily on rocky worlds. Either answer would be profound. Mars is not only a search for organisms, it is a test of how generous the universe is with life. The search for life on Mars is a search for evidence. The question is thrilling, but science cannot answer it with hope alone. Every claim must pass through careful testing, comparison, and doubt. Researchers look for patterns that cannot easily be explained by non-living chemistry. They examine rocks in context, study minerals around possible clues, and ask whether several lines of evidence point in the same direction. A single strange shape is not enough. A single molecule is not enough. Mars demands patience because ancient environments can imitate biology in surprising ways. The goal is not to find something that merely looks alive, but something whose story holds together under pressure. That is what makes the search so dramatic. The answer may be hidden in a grain of sediment or a chemical imbalance, but it must be strong enough to change our understanding of life. Wonder begins the search, but evidence must carry it home. Viking landers ran the first biology experiments on Mars. In the 1970s, 2 landers touched down on Mars and did something astonishing. They carried experiments designed to test the soil for signs of living metabolism. Tiny samples were fed nutrients, heated, or exposed to different conditions, while instruments watched for chemical responses. Some results seemed surprisingly active at first, which sparked intense excitement. But other instruments failed to detect the organic molecules that scientists expected if life were present. That conflict created one of the great puzzles in Mars exploration. The soil was clearly chemically reactive, but the cause remained uncertain. The Viking missions were bold because they asked the life question directly, not from orbit, not through distant images, but with robotic laboratories sitting on the ground. Their results did not give the final answer. Instead, they taught scientists how difficult Mars would be and how careful future life detection must become. Viking results were intriguing, but scientists still debate them. The lander experiments produced responses that still invite discussion decades later. Some researchers argue that at least one test behaved as though microbes were consuming nutrients and releasing gas. Others point out that reactive chemistry in the Martian soil could have produced similar signals without life. Later discoveries of perchlorates made that second possibility even more important, because heated Martian soil can destroy or alter organics in ways Vikings' instruments may not have anticipated. This is why the debate never became a simple yes or no. The data were real, but the interpretation remains difficult. Viking arrived before scientists understood many details of Martian surface chemistry. Its legacy is therefore both frustrating and inspiring. It may have missed life, ruled out life at its sites, or revealed unfamiliar chemistry. Whatever the truth, those experiments still echo through every mission that follows. No mission has yet confirmed living organisms on Mars. After decades of orbiters, landers, and rovers, the careful answer remains that life has not been found. That does not make Mars less interesting. In some ways, it makes the search sharper. Each mission has narrowed the possibilities, revealed ancient habitable settings, and exposed the planet's chemical complexity. Scientists have found water-shaped landscapes, buried ice, organic molecules, and minerals formed in watery environments. But none of these discoveries alone proves living cells. Confirmation would require evidence so strong that other explanations fall away. This is why language matters. A possible biosignature is not a discovery of life. A habitable environment is not an organism. Mars keeps offering clues, but not the final sentence. The suspense is part of its power. We are close enough to study the planet in detail, yet the greatest answer still remains just beyond our reach. Curiosity found methane that appears and fades mysteriously. Methane in the Martian atmosphere is one of the planet's most puzzling clues. Curiosity has detected occasional rises in methane near the surface, followed by declines that are difficult to explain fully. On Earth, much methane comes from living organisms, but it can also be produced by geology. That double possibility makes the signal fascinating and frustrating. Methane should not last forever in the Martian atmosphere because sunlight and chemistry break it down over time. If it is present, something may be releasing it relatively recently. Perhaps it escapes from underground pockets. Perhaps it comes from rock reacting with water. Perhaps there are seasonal processes we do not yet understand. The mystery deepens because orbital measurements have not always matched surface detections. Mars seems to whisper methane in irregular breaths, and scientists are still trying to learn what that whisper means. Methane on Mars could come from geology or biology. The same molecule can have very different origins. On Earth, microbes called methanogens produce methane in oxygen-poor places such as wetlands, sediments, and animal digestive systems. But methane can also form without life, especially when certain rocks react with water and heat. Mars has the ingredients for at least some non-biological pathways, which means methane would not be proof of organisms by itself. Scientists would need context. They would look for associated gases, isotope patterns, timing, location, and geological setting. A biological source might leave a different signature from a purely chemical one, but those distinctions can be subtle. This is what makes methane such a perfect Martian mystery. It is simple enough to name, yet difficult to interpret. One molecule can open two doors. Behind one is hidden geology. Behind the other is the possibility of underground life. Trace gases may reveal hidden activity beneath the surface. A planet's atmosphere can carry messages from places we cannot easily reach. Tiny amounts of gas may escape through cracks, seep from buried materials, or appear after chemical reactions in the ground. On Mars, these traces could hint at active processes below the surface, even when the landscape looks still. Scientists study gases such as methane and look for patterns in season, location, and concentration. A brief plume may point to a release event. A repeated rhythm may reveal temperature or pressure changes. The challenge is that the signals can be faint, and instruments do not always agree. Yet the idea is powerful. Mars may reveal its underground behavior not by showing us liquid water or living cells directly, but by letting a few molecules drift upward into the air. In a thin atmosphere, even a trace can become a clue worth chasing. Mars microbes, if present, might breathe chemistry instead of oxygen. Oxygen is central to animal life, but it is not required by all organisms. Many microbes on Earth live without it, using other chemical reactions to move energy through their cells. Some rely on sulfur compounds. Others use iron, carbon dioxide, hydrogen, or nitrate. This matters for Mars because its atmosphere has very little oxygen, and its most promising habitats may be underground. If Martian microbes exist, they might not resemble plants or animals in any obvious way. They might be tiny chemical specialists, drawing energy from reactions between rock, water, and dissolved gases. Their world would be dark, slow, and mineral-rich. They would not breathe air, as we do. They would exchange electrons through chemistry, quietly maintaining life at a pace almost beyond imagination. To search for them, scientists must think beyond familiar biology and follow energy wherever the planet provides it. Some Earth microbes live without sunlight deep underground. Far beneath Earth's surface, life exists in rock pores, fractures, mines, and buried water systems. These organisms do not depend on sunlight. They survive on chemical energy produced by interactions between water and minerals, sometimes growing so slowly that their lives challenge our usual sense of biology. Some communities live in isolation for astonishing lengths of time. They show that the surface is not the only realm where life can persist. This has transformed the way scientists think about Mars. If Earth's deep biosphere can thrive without daylight, then a cold, radiation-exposed planet might still shelter life below. The comparison is not perfect because Mars is smaller, drier, and harsher. Still, deep Earth microbes prove that biology can build entire hidden ecosystems away from the Sun. They make the Martian subsurface feel less like emptiness and more like an unanswered question. Terrestrial extremophiles guide ideas about possible Martian survival. Earth's toughest organisms are not Martians, but they help scientists imagine what Martian life would need to endure. Some microbes tolerate intense cold. Others survive high salt, acidity, dryness, radiation, or crushing pressure. Each adaptation offers a clue. Protective pigments can reduce damage. Dormant states can pause metabolism. DNA repair systems can undo harm after exposure. By studying these organisms, researchers learn which limits are flexible and which may be absolute. Mars combines several stresses at once, which makes it especially difficult. Cold alone is not the whole problem. Dryness, salts, radiation, and low pressure interact together. Extremophiles show that life is inventive, but they also remind us not to exaggerate. Survival in a laboratory condition does not equal thriving on Mars. Still, they are living proof that biology can stretch far beyond comfort, and that a world need not look welcoming to be worth investigating. Tardigrades are tough, but Mars would still be brutal. Tardigrades are famous for surviving extremes. They can dry into a dormant state, endure freezing, tolerate radiation, and recover when conditions improve. Their toughness makes them a popular symbol of life's resilience. Yet Mars is not merely one extreme. It is many extremes layered together. Low pressure, intense dryness, ultraviolet radiation, oxidizing soil chemistry, and deep cold would make long-term survival at the surface extremely difficult. A tardigrade might endure brief exposure under certain conditions, but enduring is not the same as living, feeding, reproducing, and forming a stable population. That distinction matters. Mars forces us to separate survival tricks from true habitability. The planet might allow some organisms to persist temporarily as dormant passengers, especially if shielded. But active life would need protection, moisture, energy, and chemistry in balance. Even Earth's toughest creatures would find the open Martian surface almost unimaginably severe. Dormant spores show how life can wait through harsh times. Some microbes can form spores, which are extraordinarily durable resting stages. In that state, metabolism nearly stops. The organism becomes protected by tough layers, and it can wait through heat, cold, dryness, chemicals, or lack of food. When conditions improve, the spore may awaken and grow again. This ability matters for Mars because the planet's history may have included long, hostile intervals between more favorable episodes. If life ever arose there, dormancy could have been a survival strategy during dry or frozen periods. Spores also matter for spacecraft cleanliness, because hardy Earth organisms can be difficult to remove completely. The idea of waiting life is powerful. It suggests biology does not always need constant comfort. It can retreat into stillness, almost like a seed beneath winter soil. On Mars, if anything ever learned to pause well enough, time itself may have become part of its survival. Martian life might be slow, sparse, and deeply buried. When people imagine alien life, they often picture something dramatic. Mars invites a humbler possibility. If life exists there today, it may be microscopic, rare, and hidden in isolated pockets below the ground. Its metabolism might be incredibly slow, limited by cold temperatures, scarce liquid water, and modest chemical energy. Whole communities could occupy tiny films along mineral surfaces or small pores in rock. Such life would not announce itself with movement or color. It might leave only subtle chemical imbalances, unusual isotopes, or faint organic patterns. Detecting it would be difficult, especially from the surface. Yet this possibility is no less profound. A sparse underground biosphere would still mean life found a second home beyond Earth. It would show that biology can shrink its needs, lower its pace, and endure inside a planet that seems dead from above. Underground aquifers would be prime habitats, if they exist. A buried aquifer on Mars would be one of the most exciting environments imaginable. Liquid water protected below the surface could offer stability, shielding, and contact with minerals. On Earth, aquifers host microbial life in dark spaces where chemistry replaces sunlight. For Mars, the key question is whether such liquid reservoirs still exist, or whether most accessible water is frozen solid. Radar studies and geological clues have raised possibilities in some regions, though interpretations can be disputed. If underground liquid water is present, its saltiness, temperature, and chemistry would decide whether it could support life. It might be too briny for known organisms, or it might contain small zones where biology could persist. The reason scientists care so much is simple. A subsurface aquifer would gather several essentials in one protected place. In the search for living Mars, few targets would be more compelling. Ancient groundwater may have connected lakes beneath the Martian surface. Not all Martian water had to flow in rivers under open skies. Some may have moved underground, linking basins through hidden pathways in the crust. Groundwater can seep, rise, dissolve minerals, fill low places, and leave deposits behind as it changes chemistry. On Mars, this could explain why some separated basins show signs of related water levels or similar mineral histories. Imagine a planet where lakes on the surface were only the visible parts of a larger underground system. Water might have moved slowly through fractured rock, emerging in springs or feeding crater lakes from below. Such networks would matter for life because they create protected roots and connected habitats. Microbes, if present, could have occupied subsurface waters even when surface lakes dried. This hidden plumbing gives ancient Mars more depth. Its watery past may have been not only seen in channels, but felt beneath the ground. Salt minerals can trap tiny pockets of ancient fluid. When salty water evaporates, it can leave minerals behind. Sometimes those minerals grow around microscopic droplets, sealing tiny bits of fluid inside crystal structures. On Earth, such inclusions can preserve ancient water chemistry for immense lengths of time, and sometimes even protect organic material or microbial remains. Mars has salt deposits that formed as watery environments dried out, which makes them scientifically tempting. A salt crystal might hold a miniature sample of a vanished lake or groundwater system. Inside it could be clues about acidity, temperature, dissolved gases, and chemical ingredients. The scale is almost poetic, though the science is very real. A whole ancient environment may be reduced to a trapped droplet smaller than a grain of dust. If future missions can study these minerals carefully, they may open tiny sealed windows into the last moments of Martian water. Martian caves could protect life from radiation and temperature swings. A cave on Mars might be more than an empty hollow. It could be a natural shield. Beneath rock, the worst radiation from space would be reduced, and the daily swing between warmth and bitter cold would be softened. That matters because stability is precious on a planet where the open surface is so harsh. On Earth, caves can preserve delicate minerals, ancient climate records, and living communities adapted to darkness. Mars may have similar underground spaces, carved by lava, collapse, or ancient geological stress. If microbes ever found shelter there, they would have been hidden from the damaging conditions above. Even if no life remains, caves may protect chemical traces better than exposed ground. They are hard to reach, hard to explore, and deeply tempting. A dark opening on Mars may be an entrance into one of the planet's safest memory chambers. Lava tubes may become shelters for astronauts and microbes. When lava flows, its outer surface can cool and harden while molten rock continues moving underneath. After the flow drains away, it may leave a long tunnel behind. Mars almost certainly has such lava tubes, and they could be enormous because of lower gravity and large volcanic flows. For future explorers, these tunnels are exciting because they offer natural protection from radiation, micrometeorites, dust storms, and extreme temperature changes. Instead of building every wall from scratch, astronauts might use the planet's own geology as shelter. For scientists, lava tubes are also intriguing because they may preserve stable microenvironments. Ice could remain trapped inside. Minerals could record past fluids. If life ever entered such spaces, it might have found one of the more forgiving habitats on Mars. These tunnels join two stories at once. They are possible homes for future humans and possible vaults for older Martian clues. Mars has skylights that may open into hidden caverns. From orbit, scientists have seen dark circular pits on Mars that look like holes in the surface. Some may be collapsed roofs of underground voids, opening into lava tubes or cavern systems below. These features are called skylights, and they are thrilling because they offer rare access points into the hidden interior. The darkness inside is difficult to interpret from above. It may be a shallow pit, or it may lead into a deeper chamber where ice, dust, and protected rock wait unseen. A skylight is not dramatic in the usual sense. It may look like a black dot on a plane. But that dot could mark a doorway into a different Mars, one less exposed to radiation and weather. Future missions may treat these openings with great care. A single descent into one could reveal a preserved environment that orbiters can only hint at. Future robots may explore caves for preserved biosignatures. Exploring Martian caves will not be easy. Rovers are built for surfaces where sunlight, radio communication, and careful driving are possible. Caves bring darkness, uneven ground, steep entries, dust, and uncertain communication. That is why future robots may need new designs. Some could hop, climb, crawl, fly, or lower instruments by cable into openings. Their goal would be to search places where ancient traces may have escaped the damage found on exposed ground. Protected walls might hold mineral coatings. Floors might preserve ice. Fine sediments could contain organic chemistry sealed away from radiation. The mission would feel almost like space exploration inside space exploration, a robot entering darkness on another world to search for signs that something once lived there. Even if it found no biology, it would open a new chapter in Mars science. Caves may be among the last great unexplored habitats of the Red Planet. Biosignatures can be chemical, mineral, structural, or isotopic. A sign of life is not always a tiny fossil, shaped like a cell. Sometimes the evidence is more subtle. It might be a pattern of carbon molecules that looks difficult to make without biology. It might be a mineral structure formed when microbes changed their surroundings. It might be layered textures built by living mats, or isotope ratios that suggest organisms preferred lighter versions of an element. This variety is why searching for life is so demanding. Scientists do not look for one magic clue. They look for relationships between chemistry, geology, and environment. A possible biosignature becomes stronger when several kinds of evidence point together. It becomes weaker when ordinary geology can explain it. Mars may hold clues that are not obvious to the eye at all. The most important discovery might arrive as a pattern in a laboratory graph, quiet but world-changing. False biosignatures make Mars science careful and slow. Nature is very good at imitation. Minerals can grow into shapes that resemble cells. Chemical reactions can create patterns that seem organized. Carbon compounds can form without organisms. Even layered rocks can look biological when they are simply records of water, wind, or chemistry. This is why Mars scientists move cautiously. They know that a mistake would be damaging, especially with a claim as important as alien life. Every promising clue must be tested against non-living explanations. Could heat have made it? Could water have arranged it? Could radiation have altered it? Could contamination have introduced it? This careful pace may feel frustrating, but it is what gives a discovery strength. Mars asks for wonder, but it also asks for discipline. The goal is not to announce life quickly. The goal is to find evidence so clear that doubt has fewer and fewer places to hide. Tiny mineral patterns can mimic the shapes of fossils. A strange shape in rock can fool the imagination. On Earth and Mars alike, minerals sometimes grow as spheres, tubes, filaments, or branching forms. Under a microscope, these can look surprisingly lifelike. They may resemble bacteria, shells, or tiny colonies, even when no organism was involved. This happens because chemistry can organize matter beautifully. Crystals grow along gradients. Fluids move through pores. Minerals deposit around bubbles or fractures. The result can feel biological without being biological. This is especially important for Mars, where any possible fossil would likely be very small and very ancient. Scientists cannot trust shape alone. They must ask what the structure is made of, how it sits in the rock, and whether surrounding chemistry supports a living origin. A tiny curve or tube could be a fossil, or it could be geology wearing a mask. Scientists need return samples to test Martian clues properly. Rovers are extraordinary, but they are still limited by size, power, and distance. A laboratory on Earth can do far more. It can slice rocks into ultra-thin sections, measure chemistry with remarkable precision, compare isotopes, search for organic structures, and repeat tests with different instruments. That is why returning Martian samples is so important. The question of life may depend on details too small or too complex for a rover to settle alone. A sealed core from the right place could be studied by teams around the world for decades. New tools could examine it years after it arrived. The sample would become a scientific treasure, not because it guarantees an answer, but because it allows the strongest possible testing. Mars may have already offered clues. To understand them fully, we may need to bring a carefully chosen piece of that world home. Mars sample return could transform astrobiology in one generation. Bringing rocks from Mars to Earth would be one of the most ambitious scientific achievements ever attempted. It would connect robotic exploration, orbital capture, planetary protection, and laboratory science into one long chain of precision. The reward could be enormous. Samples chosen from ancient lakebeds, deltas, or altered rocks might contain records that no rover can fully decode. Astrobiology would move from remote measurement to direct investigation. Scientists could test whether possible biosignatures are real, whether organic molecules have meaningful patterns, and whether Mars preserved habitable environments in detail. Even a lifeless sample would be valuable because it would teach us how far prebiotic chemistry can go on a neighboring planet. A returned Martian rock would not be a museum curiosity. It would be a piece of another world placed under humanity's best instruments, asking whether life is common, rare, or still unknown. Perseverance stores sealed cores for future laboratories on Earth. The rover does something wonderfully patient. It drills into carefully chosen rocks, places slender cores into clean tubes, seals them, and stores them for possible return. Each tube is like a message prepared for scientists who may not open it for years. The samples come from places selected because they record different parts of Jezero crater's history. Some may represent lake sediments. Others capture igneous rocks, altered minerals, or materials moved by ancient water. This diversity matters because one rock cannot tell the whole story. A set of cores can reveal how environments changed across time. The sealing process also helps protect the samples from contamination and preserves their context. Perseverance is not only exploring Mars for itself, it is curating a future archive. Somewhere inside those tubes may be the clearest clues yet gathered about whether the crater was merely habitable or something more. Earth laboratories can detect clues rovers cannot measure. A rover must carry a miniature science lab across rough terrain on another planet. That is a miracle, but it is also a compromise. Instruments must survive launch, landing, dust, cold, limited power, and remote operation. Earth laboratories do not face those same limits. They can use large machines, delicate preparation methods, and many independent techniques on the same sample. They can detect tiny isotope differences, map organic molecules in fine detail, and image structures far smaller than a rover can resolve. They can also repeat experiments when results are confusing. This matters because life detection may depend on subtle patterns rather than obvious fossils. A Martian sample could look ordinary until a laboratory reveals unusual chemistry locked inside it. The greatest discoveries often come from precision. Mars may not shout its secrets from the surface. It may require the full, quiet strength of Earth's laboratories to hear them. Planetary protection keeps Earth microbes from confusing Mars discoveries. When humans send machines to Mars, they must also worry about what travels with them. Earth microbes can be remarkably stubborn. Some survive dryness, cold, cleaning, and long storage. If they hitchhiked on a spacecraft and later appeared in a sample or habitat, they could create a terrible scientific confusion. A discovery that looked Martian might actually be terrestrial contamination. Planetary protection exists to prevent that. It includes careful cleaning, controlled assembly spaces, biological monitoring, and mission rules that depend on where a spacecraft will go. The goal is not only to protect Mars from Earth, it is to protect the truth. If we ever find life or possible life there, we need to know it belongs to Mars. The cleanliness of a spacecraft may seem like a technical detail, but it is part of the deepest question. We must not bring the answer with us by accident. Spacecraft are cleaned carefully before touching Martian soil. Before a lander or rover leaves Earth, engineers treat it almost like a surgical instrument. Parts are cleaned, baked, wiped, tested, and assembled in controlled rooms. The goal is to reduce the number of biological hitchhikers that could survive the trip. This is difficult because spacecraft are complex. They have seams, electronics, wheels, drills, cables, and hidden surfaces where particles can cling. Cleaning must also avoid damaging delicate instruments. Every mission balances scientific ambition with contamination control. Places that might contain liquid water or special habitability potential require even stricter care. The reason is simple. Mars exploration is not only about reaching a planet, it is about reaching it responsibly. A rover wheel rolling through dust should carry instruments, not a secret sample of Earth biology. Careful cleaning makes future discoveries more trustworthy, and it keeps the search for Martian life from becoming a mirror of ourselves. Human explorers will make contamination harder to control. Robotic missions can be sterilized and monitored with great care. Humans cannot. We carry trillions of microbes in our bodies, on our skin, in our breath, and throughout every living system that keeps us healthy. Any crewed mission to Mars would bring habitats, waste systems, air recycling, food production, tools, suits, and repairs. Each one creates possible pathways for Earth life to escape into the environment, or for Martian material to enter human spaces. This does not mean humans should never go. It means the search for native Mars life becomes more urgent and more complex before they arrive. Scientists may need to study the most sensitive sites robotically first. Astronauts will require strict procedures around sampling and exploration. The irony is powerful. The people best able to investigate Mars with intelligence and flexibility may also be the hardest visitors to keep biologically separate from it. Astronaut habitats may need closed ecosystems to survive there. Living on Mars would require more than walls and oxygen tanks. A long-term habitat would need systems that recycle air, water, nutrients, and waste with extreme efficiency. On Earth, nature performs these cycles across oceans, forests, soils, and the atmosphere. On Mars, explorers would need to build small versions of those cycles inside sealed spaces. Carbon dioxide would be removed or reused. Water would be recovered from breath, hygiene, and waste. Food scraps could become nutrients. Microbes might help process materials. Plants or algae could contribute oxygen and food, though they would need careful control. The habitat would become a tiny managed biosphere, part machine and part living system. This is one of the most fascinating parts of Mars's exploration. To keep humans alive on a lifeless surface, we may have to carry a miniature Earth with us. Plants on Mars would need pressure, warmth, and shielding. A seed placed in Martian soil under the open sky would not simply grow into a little green miracle. The surface lacks the pressure, temperature, and protection that plants require. Water would be unstable, radiation would damage tissues, and the cold would be severe. To farm on Mars, humans would need controlled environments. Greenhouses or growth chambers would provide air pressure, warmth, moisture, nutrients, and filtered light. They would also shield crops from radiation and keep dust from interfering with equipment. Plants might still face challenges, including lower gravity and limited resources, but biology is adaptable when conditions are managed. The vision is beautiful because it is not magic. It is engineering in service of life. A leaf on Mars would represent atmosphere, water, chemistry, and human care working together. Every sprout would be a small declaration that Earth's living systems can travel. Martian soil contains nutrients, but also troublesome reactive salts. The loose surface material on Mars is often called soil, though it lacks the rich biology of Earth soil. Chemically, it contains elements plants need, including forms of nitrogen, phosphorus, potassium, and trace minerals. That sounds promising, but the story quickly becomes more complicated. It also contains reactive compounds, including perchlorides, that can be harmful to plants and people if not handled properly. The texture, chemistry, and lack of organic matter would all need adjustment before crops could thrive. Future farmers might wash the material, mix it with composted biomass, add beneficial microbes, or use hydroponic systems instead. This makes Martian agriculture less like planting a garden and more like building a living chemistry project. The ground offers ingredients, but not an easy welcome. To grow food there, humans would need to transform raw regolith into a carefully managed support system for life. Greenhouses could turn Martian sunlight into food and oxygen. A Martian greenhouse would be more than a place to grow crops. It could become part of a survival system. Plants use light, carbon dioxide, and water to build sugars, releasing oxygen as they grow. Mars has carbon dioxide in abundance, and sunlight still reaches the surface, though weaker than on Earth. With pressure, warmth, shielding, and careful water recycling, a greenhouse could convert local conditions into something useful for humans. It would not be simple. Dust storms could dim the light. Radiation would need blocking. Leaks would be dangerous. Nutrients would need constant management. But the principle is profound. A sealed structure filled with green life could take the raw materials of Mars and turn them into breath and nourishment. In a world of red dust and thin air, a greenhouse would be both farm and life support, a pocket of biology shaped by human hands. Cyanobacteria may one day help produce resources on Mars. These tiny organisms changed Earth forever. Long ago, cyanobacteria helped fill our atmosphere with oxygen through photosynthesis. On Mars, they are being studied not because they could simply be scattered on the ground, but because they might work inside controlled systems. With the right pressure, water, nutrients, and protection, they could help produce oxygen, biomass, or useful chemicals. Some research explores whether hardy strains could use ingredients available on Mars, including carbon dioxide, light, and processed local materials. Their value lies in efficiency. A living culture can grow, reproduce, and turn simple inputs into biological products. That makes cyanobacteria potential partners in future life support. They would not terraform Mars by themselves, and they would need care. But in a habitat or bioreactor, these ancient microbes could help humans live farther from Earth, carrying one of our planet's oldest biological talents to another world. Terraforming Mars remains far beyond current human ability. Turning Mars into a second Earth is one of the grandest ideas in science fiction. But the real planet is stubborn. It has too little atmosphere, too little accessible warming power, no strong global magnetic shield, and immense environmental challenges. To terraform it, humans would need to thicken the air, raise temperatures, stabilize liquid water, manage radiation, and create conditions that could last. Current technology cannot do this on a planetary scale. Even releasing available carbon dioxide may not provide enough greenhouse warming to make Mars broadly habitable. That does not make the dream useless. It helps reveal how delicate Earth truly is. Our planet's habitability depends on gravity, atmosphere, magnetic protection, oceans, biology, and long-term climate balance working together. Mars shows how hard such a system is to rebuild once lost. For now, any human life there will live in shelters, not under an open blue sky. Mars cannot simply be warmed into another Earth today. It is tempting to imagine Mars waiting for us to restart it, as if a little heat could awaken oceans, clouds, and forests. The reality is far more difficult. Mars does not seem to have enough easily available atmosphere to create Earth-like pressure. Much of its carbon dioxide is locked away, lost to space, or present in amounts too small for a planetary rescue. Warming the surface would also not solve radiation, low gravity, global dust, or the absence of a strong magnetic shield. Even if temperatures rose, liquid water would still need stable pressure and long-term protection. This makes Mars fascinating in a humbling way. It is close enough to study, and perhaps to visit, but not easily transformed. The planet reminds us that Earth is not just warm rock. It is a rare balance of air, water, magnetism, chemistry, and life. Its low gravity may limit any restored atmosphere. Mars has only about a third of Earth's gravity, and that changes what a planet can hold on to. A stronger world grips gases more tightly. A smaller one lets them escape more easily over geological time. Mars can keep an atmosphere, but holding a thick, warm, Earth-like one for immense ages would be a major challenge. Any attempt to restore air would have to fight the same long-term losses that helped shape the planet we see today. Gas molecules can leak away, especially when the upper atmosphere is heated and struck by particles from the sun. Low gravity also affects dust movement, human bodies, engineering, and possibly how future ecosystems would function. It is not a small detail. It is part of Mars's identity. The planet is not merely cold because it lacks warmth. It is small enough that keeping a protective sky becomes difficult. Life on Mars might begin with human-made habitats. If living systems flourish on Mars in the future, they may not begin in open valleys or beneath a natural sky. They may begin inside carefully sealed structures built by humans. A habitat could hold pressure, warmth, water, breathable air, and protection from radiation. Within it, microbes, plants, and people might form a managed web of survival. This would not be Mars becoming Earth. It would be Earth life creating tiny islands of habitability on Mars. The first truly active Martian biology may be a tray of seedlings, a tank of algae, a culture of useful microbes, or a human microbiome carried across space. That thought is quietly astonishing. Life may not only be something we search for on Mars. It may become something we bring there, protect there, and ask to grow there under conditions that the planet itself does not naturally provide. The first Martian ecosystems may live inside sealed rooms. An ecosystem does not have to be a forest or ocean. It can be a carefully balanced room where air, water, microbes, plants, and machines work together. On Mars, the first ecosystems may be artificial, small, and intensely monitored. Nothing could be wasted. Carbon dioxide from human breath might feed plants. Plant waste might feed microbes. Water would be cleaned and reused again and again. Sensors would track gases, nutrients, humidity, and contamination. Such a system would be fragile, but it would also be beautiful in its precision. It would turn survival into a living circuit. Every leaf would matter. Every drop would be counted. Every organism would have a role. In that room, Mars would still be outside, cold and dusty. But inside, life would fold itself into a new shape, not wild yet, but present, breathing, and beginning. Future settlers could farm microbes before growing larger crops. The first Martian farms may not look like fields. They may look like tanks, tubes, filters, and glowing bioreactors. Microbes are efficient, compact, and versatile. Some can help recycle waste. Others can produce nutrients, oxygen, fuels, plastics, medicines, or soil additives. Before settlers rely on wheat, potatoes, or fruiting plants, they may depend on microscopic workers that grow quickly and require less space. This would make sense on a planet where every kilogram of equipment and every liter of water matters. Microbial farming could turn simple inputs into useful outputs with impressive efficiency. It could also prepare materials that make later plant growth easier. In a strange way, Mars settlement may begin by honoring Earth's smallest life forms. The future may not arrive first as a garden under glass. It may arrive as a controlled culture of microbes quietly making survival possible. Martian water ice may become drinking water and rocket fuel. Buried ice could be one of the most valuable resources on Mars. For astronauts, it could provide water to drink, wash with, grow plants with, and split into oxygen and hydrogen. Those same ingredients could support breathing systems and help make propellant for return journeys or future exploration. This is why ice deposits are not just scientific curiosities. They may decide where humans can land and how long they can stay. A mission that uses local water does not need to bring every drop from Earth. That changes the scale of possibility. The challenge is finding ice that is clean enough, accessible enough, and located in safe terrain. Extracting it would require machines that dig, heat, collect, purify, and store. In the story of human Mars exploration, water ice may become the first true Martian treasure. Not gold, not gems, but survival itself. Oxygen can be made from the carbon dioxide atmosphere. Mars has very little oxygen in its air, but it has plenty of carbon dioxide. That is useful because carbon dioxide contains oxygen atoms locked together with carbon. With the right technology, those atoms can be separated. For astronauts, making oxygen locally would be enormously valuable. It could supply breathable air and help produce rocket oxidizer, which is needed for burning fuel. This idea turns the thin Martian atmosphere from a problem into a raw material. Instead of hauling all oxygen from Earth, explorers could manufacture some of it where they are. The process requires power, equipment, and reliability, but the principle is powerful. Mars may not give humans an atmosphere they can breathe, yet it offers the ingredients for one of the things they need most. Survival there may depend on learning to take the planet's chemistry apart and rebuild it into something useful. Moxie proved oxygen production is possible on Mars. A small golden instrument aboard Perseverance performed an experiment that felt like a doorway to the future. It took in Martian air, processed carbon dioxide, and produced oxygen. The amounts were modest, but the meaning was enormous. This was not a laboratory simulation on Earth. It happened on Mars, using the real atmosphere, under real conditions. The device showed that local resource use is not only an idea on paper, it can work on the planet itself. Future systems would need to be much larger, more durable, and capable of operating for long periods. But every major technology begins with proof. Moxie was like a first breath made by a machine on another world. It did not make Mars habitable. It did something more practical, and perhaps more important. It showed that future explorers may be able to create a piece of their life support from Martian air. Mars farming would need biology, engineering, and patience. Growing food on Mars would be one of the most complex acts of survival ever attempted. Plants would need controlled pressure, reliable warmth, clean water, balanced nutrients, filtered light, and protection from radiation. Engineers would design the chambers, pumps, sensors, and recycling systems. Biologists would choose crops, microbes, and growth strategies that can tolerate unusual conditions. Farmers would become technicians, ecologists, and caretakers at once. Every seed would represent a small risk and a small promise. The soil or growth medium would need preparation. Pollination might need help. Disease would have to be watched closely because a closed habitat has little room for mistakes. Yet the reward would be profound. Food grown on Mars would not only feed bodies, it would feed morale. A fresh leaf in a red desert would remind explorers that life can be carried, tended, and renewed far from home. Human life on Mars would depend on Earth at first. The earliest explorers would not be independent pioneers in the romantic sense. They would rely on Earth for equipment, spare parts, medicine, communication, scientific support, and probably much of their food. Every habitat system would need backup. Every machine would matter. A broken pump, torn seal, or failed heater could become urgent in a place where the outside environment cannot support human life. Over time, settlers might learn to make more materials locally, recycle more efficiently, and grow more food. But the first stages would be deeply connected to home. Mars would stretch human ability, not replace Earth's importance. This dependency gives the story emotional weight. To live there would be to stand on another planet, while still belonging to this one. Every message, shipment, and instruction would cross space as a reminder that the first Martians would survive through a partnership between two worlds. A Martian day is only slightly longer than Earth's. A day on Mars is called a sol, and it lasts just a little longer than an Earth day. That small difference is one of the friendliest features Mars offers to human explorers. It means sleep, work, lighting, and daily routines could follow a rhythm that feels surprisingly familiar. Rover teams on Earth have sometimes lived on Martian time while operating missions, shifting their schedules later each day to match sunrise and sunset on the planet. For astronauts, the sol would shape everything from power use to greenhouse lighting and outdoor activity. It would not make Mars easy, but it would make its clock feel less alien. In a world where the air cannot be breathed and the cold can be severe, this near match is almost comforting. Mars turns beneath the sun in a rhythm close enough that human bodies might learn its days. Mars has two tiny moons racing across its sky. Phobos and Deimos are not grand moons like ours. They are small, dark, irregular bodies, more like captured fragments than perfect spheres. From the Martian surface, Phobos would move quickly across the sky because it orbits so close to the planet. It can rise in the west and set in the east, crossing overhead in only a matter of hours. Deimos is farther away and slower, appearing smaller and more distant. These moons would make the Martian sky feel subtly unfamiliar. They cannot produce the same bright moonlit nights Earth knows, but they bring motion, eclipses, and mystery. Their origins are still debated. They may be captured asteroids, or they may have formed from debris after a giant impact. For future inhabitants, these moons would be more than scenery. They would be landmarks, timekeepers, and possible stepping stones for exploration. Phobos may one day break apart into a ring. Mars's larger moon is slowly moving closer to the planet. Tidal forces are drawing it inward, and one day it may cross a limit where Mars's gravity begins to tear it apart. The result could be dramatic. Instead of a moon, Mars may gain a temporary ring made from shattered fragments of Phobos. This would not happen soon by human standards. It lies millions of years in the future, but it reveals that even the Martian sky is changing. Phobos already bears long grooves and a battered surface, signs of stress, impacts, and a violent history. Its fate adds a strange beauty to the Mars story. A small moon that once raced above dusty plains may eventually become a necklace of debris around the planet. Future Mars, far beyond us, could wear rings where its closest moon once flew. Martian sunsets look blue because dust scatters light differently. On Earth, sunsets often glow red and orange because our atmosphere scatters blue light away from the direct path of the sun. Mars has a much thinner atmosphere, but it is filled with fine dust. That dust changes the colors in an unusual way. During the day, the sky can appear butterscotch or pinkish because dust scatters reddish light through the air. Near sunset, light travels through more of that dusty atmosphere, and the region close to the sun can take on a bluish glow. The effect is delicate and otherworldly. Rovers have photographed it from the surface, giving humans a view no eye had ever seen before space exploration. A sunset on Mars is not simply Earth's sunset painted red. It follows its own optical rules. Even light behaves differently there, turning the end of day into a small lesson in alien weather. The red planet is red because its surface is rusty. Mars gets its famous color from iron minerals in its dust and rocks. When iron reacts with oxygen, it can form oxides, similar in broad idea to rust on Earth. These minerals spread across the surface as dust, tinting the planet in shades of red, orange, and brown. That color has shaped human imagination for thousands of years. Ancient observers saw a blood-colored wanderer moving among the stars. Modern spacecraft revealed that the redness is not supernatural at all, but geological. It tells of chemistry, weathering, and fine particles carried by wind. The red dust can settle on rover decks, coat solar panels, and soften the appearance of distant hills. Beneath it, Mars is not all one color. There are darker volcanic sands, pale minerals, and layered rocks. Still, the rusty surface gives the planet its identity, making it instantly recognizable across the night. Mars has auroras, even without a global magnetic field. Earth's auroras are guided by a strong global magnetic field, which funnels charged particles toward polar regions. Mars is different. It lacks that planet-wide shield, yet it can still produce auroras. The key lies in patches of ancient magnetism preserved in the crust, along with interactions between the atmosphere and particles from the sun. Some Martian auroras are ultraviolet, invisible to human eyes without instruments. Others may occur in unusual patterns because the magnetic environment is so fragmented. This makes Mars a fascinating laboratory for space weather. Its auroras are not the sweeping polar curtains we know from Earth. They are signs of a planet whose old magnetic field is gone, but not entirely forgotten. The crust still carries pieces of magnetic memory, and the sun still stirs the upper air. Even without a global shield, Mars can glow in response to space. Ancient Mars may have smelled metallic, dusty, and sharp. No human has breathed Martian air, and without a suit, it would be fatal. But scientists can imagine certain sensory impressions from chemistry. The air is mostly carbon dioxide, extremely thin and cold. The dust contains iron oxides and reactive salts. If a sample were safely brought into a controlled environment and smelled indirectly through instruments or filters, it might suggest dry minerals, metal, and a harsh chemical sharpness rather than anything earthy or green. The ancient planet, when wetter and more active, may have had different scents near volcanic regions, salty basins, or mineral-rich mud. Smell is rarely discussed in planetary science, but it makes Mars feel strangely real. A world is not only what it looks like. It has textures, grains, gases, and chemistry. Even an imagined scent can remind us that Mars is a physical place, not just a red dot in the sky. Any Martian microbe would rewrite biology's deepest questions. A single cell from Mars would be more than a discovery. It would become a comparison point for all life on Earth. Scientists would want to know whether it uses DNA, proteins, membranes, and familiar chemistry, or whether it follows a different biological logic. If it resembled Earth life closely, that might suggest exchange between the planets or shared origins. If it was truly independent, the implications would be even greater. It would mean life can begin more than once in one solar system. Biology would no longer be a single example from one world. It would become a broader cosmic process. Every textbook would change. Questions about evolution, genetics, and life's definition would deepen overnight. The organism itself might be microscopic, but the meaning would be enormous. One tiny Martian life form could turn Earth biology from the whole story into only the first known chapter. Finding dead life on Mars would still be revolutionary. Some people imagine that only living organisms would matter. But evidence of extinct Martian life would be one of the greatest discoveries in history. It would show that life began beyond Earth, even if it later disappeared. That alone would transform our understanding of the universe. Fossil microbes, preserved chemical patterns, or ancient biological minerals would reveal that Mars once crossed the threshold from chemistry into biology. Scientists could compare that vanished life with Earth's living systems and ask whether they shared a family tree. They could study how long it survived, what environments supported it, and why it ended. Extinction would not make the discovery sad only. It would make it profound. Mars might become a planet that once had a term living chapter, now closed but still readable in stone. A dead biosphere would still prove that life is not Earth's possession alone. Finding living Mars life would mean biology happened twice. This would be the discovery that changes almost everything. If scientists found living organisms on Mars and proved they arose independently from Earth life, the message would be staggering. Life would not be a rare accident confined to one blue planet. It would be something the universe can do more than once, even within the same small neighborhood, around one ordinary star. The search for life on icy moons, distant exoplanets, and ancient worlds would take on new urgency. Every place with water, chemistry, and energy would feel more alive with possibility. The discovery might be microscopic, hidden in briny pores or deep rock, but its meaning would reach across galaxies. We would look at the night sky differently, not as a silent backdrop, but as a field of chances. Mars would become the second candle in the dark, proving that biology is not alone. And so, our journey across Mars comes to rest. We have wandered through ancient lakes and river deltas, over dusty plains, beneath buried ice, and into the shadowed possibility of caves and hidden water. We have imagined a younger Mars, where the air was thicker, where rivers moved through valleys, and where chemistry may have gathered patiently in mud, stone, and mineral-rich water. We have followed rovers as they searched the ground, sealed samples, and listened for clues in rock and air. We have wondered about microbes, fossils, methane, underground shelters, and the fragile future of human life beneath sealed habitats and glassy greenhouses. Mars remains silent for now, but not empty of meaning. It is a world of questions. A red lantern in the dark, carrying the memory of water, the promise of discovery, and the possibility that life may not belong to Earth alone. If you enjoyed this sleepy journey, you're welcome to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. And if you happen to still be awake, there should be another gentle video waiting on the screen for you. But for now, let the red dust settle. Let the stars grow soft in your mind. Let your shoulders loosen, and let your breathing slow. There is nothing more you need to follow, nothing more you need to hold. Just allow the thought of that distant planet to drift away, smaller and softer, until it becomes only a quiet glow beyond the edge of sleep. Sleep well, and good night.